So welcome back. I hope you've seen my two videos on sections 3.2, one where I showed conformations of ethane with the model and one where I followed up with drawing. I'm going to move on now and do 3.3, which is conformations of bigger molecules. Butane will be our example. And I figured out that my old model kit was too big for this environment, so I switched to a smaller one. Let me show you what we did with ethane. The conclusion was that the most stable conformation of ethane was this staggered one. I'm having a hard time deciding which is left and which is right here now. There we go, staggered. If I rotate the front, eclipsed, staggered, eclipsed, staggered. So the energy keeps oscillating up and down and up and down, but the more stable conformation is the staggered one, where the bonds in the back are as far as possible from the bonds in the front. The molecules are going to spend most of their time in that conformation. If I look at a realistic grouping of molecules, many more of them will be staggered than eclipsed. But what I'm going to do now is change it to butane. So instead of having 2 carbons, I am going to make sure that I have 4 carbons in a row, like this. Now there is a conformational change possible around all the carbon-carbon bonds. I can rotate around any carbon-carbon bond. We're going to stay focused though. We're just going to focus on one carbon-carbon bond, the one in the center here. And we're going to look conformations around the side. When I switch to drawing, I'm going to start with this side-on perspective drawing. But as before, I think it's going to be more useful for us to switch on to an end view and look at Newman projections. Where is my camera looking at me from? So I think that perspective drawing turned into a Newman projection and it looks like this. And on the front carbon, I can see that there's one bond straight down. The other 2 look like they're at the corners of a triangle. On the back, same thing. One up and the other 2 at the corners of a triangle. But the bonds in the front are in between the bond in the back. That's a staggered conformation. Now I'm going to start to do the 60-degree rotations of the one in the front. I'm going to hold the back fixed and rotate the front 60 degrees. And because I'm backwards here in my camera, that was probably counterclockwise. But anyway, you can see, as before, when I do a 60-degree rotation, I went from a staggered to an eclipsed form, high energy. Another 60 degrees, staggered conformation, low energy, eclipsed, high energy, staggered, low energy, and so on and so on and so on. But this time, not all the staggered conformations are the same energy. One of the staggered conformations has the methyl group in the front opposite the methyl group in the back. And this is a special kind of staggered conformation called an anti-conformation. Anti as a word means against or opposed to. So opposed to, as far away from, that's the anti-conformation. If I rotate it though to get the other staggered conformation, again, the bonds in the back are between the bonds in the front. This is different though. Now the methyl groups are right next to each other in a staggered conformation. And we call this a gauche conformation, which is spelled like the French word for left. I don't know why. G-A-U-C-H-E. That's a gauche conformation. These methyl groups are gauche to each other. As a staggered conformation, this is still an energy minimum, but it's not the global minimum for you calculus fans in the house. This is less stable than the anti-conformation because these big groups are going to start to get in each other's way. So that's the 2 staggered conformations. Now the eclipse conformations look different. There's no special names for them, but this eclipsed conformation I would describe as saying that the hydrogen on the front eclipses the methyl in the back. There is another another eclipsed conformation though, that has the methyls eclipsing each other. Both eclipsed conformations are less stable than any staggered conformation, but one of these eclipsed conformations is less stable than the other. I told you before, it's bad when the groups get in each other's way. We call that steric hindrance. S-T-E-R-I-C, steric hindrance. And that comes from the same root as the word stereo. It talks about 3D. So in other words, there's steric hindrance here because these methyl groups are getting into each other's space. That is the highest energy conformation of butane that there is. Not only is it eclipsed, it's eclipsed with the greatest steric hindrance. The methyl groups are eclipsing each other. Again, no special name for those eclipsed conformations. I have to describe what's eclipsing what. So looking now as I go through rotation here, let's start with the most stable, staggered conformation. It's staggered and the methyl groups are anti to each other. So here we go, 60 degrees from the front, eclipsed, an energy maximum, but not the global maximum. I only have a hydrogen eclipsing a methyl, high energy. Another 60 degrees, staggered, low energy. Another 60 degrees, eclipsed, high energy, highest energy. The methyl groups are getting in each other's way. Next conformation, staggered, eclipsed, staggered, as it spins 360 degrees. I will show you on the drawing how the energy changes as a function of that rotation, but I want to show you one more thing before I sign off for this part. The most stable conformation of butane is with the methyl groups anti to each other in the staggered conformation. Staggered, least repulsion between the bonds, anti, least steric hindrance, things aren't getting in each other's way. What that means then, if I take this back and turn it back into a perspective drawing, it looks like this, or another slight adjustment, it looks like that. Now you'll remember the other day I drew skeletal structures for alkanes that showed zigzag lines. Guess why? Because that is the most stable conformation of alkanes. So even if we go on to bigger alkanes, you'll see that the most stable conformation is this zigzag backbone. Doesn't have to be the only way to draw it though. There's more than one conformation. I could draw my alkane like that. It just won't be as stable as if I draw it like that. Okay, friends,